Hello everyone, today we'll be starting chapter 16, Kinematics of a Rigid Body. So we're going to talk about kinematics. We have previously talked about kinematics and kinetics, but we were focusing on a particle. Here, for the first time in this semester, we are going to talk about a rigid body, which means that the size of the object is no longer negligible, and we are going to include the size of the particle, which means that we are going to deal with the rotation and the moment as well. Kinematics deals with the motion of an object. So we're going to start with kinematics, and then we move to kinetics, which deals with the forces that cause that motion. So there are three types of rigid body motion. That we are going to discuss here. The first one is translation, which was also present for in kinematics of a particle as well. The translation of a rigid body can be either rectilinear or curvilinear. For rectilinear motion, we usually use Cartesian coordinate system. For curvilinear motion, we usually use polar or tangential and normal coordinate system. But both of them are categorized as a translation. So this is the same whether we're talking about particle or rigid body. We have translation. For a rigid body, let's say this is our rigid body. Translation means just the displacement from location A to location B. It can be rectilinear, or we can have a curvilinear motion as well, if our object is following a curvature motion. The second type that we are gonna talk about, let's call it 2, is rotation. This is new to us. We can only talk about rotation because you're not neglecting the size. So for our object, rotation about a fixed point, our object is rotating. And then the third type of motion is general, which is the combination of translation and rotation. So let's start with rotation, the new type of motion that we deal with. So we're going to talk about rotation about a fixed point. Let's say we have a disk here. And our disk has a radius of r. Let's call it displacement of d theta. And then this displacement would be ds. So r d theta ds. The angular position, because we are talking about rotation, is shown by theta. The displacement means the change in angular position would be the displacement. And we show it by d theta or delta theta. Then the next definition would be the angular velocity. So the definition of velocity has not changed. It's just displacement over time. Here, displacement is angular displacement, but it follows the same definition, d theta over dt, which we call it theta dot. The same theta dot in polar coordinate system. But over there, theta dot was changing the position. Here we are talking about a rotation, about a fixed point. The unit is radian per second. It could be degree per second or revolution per second. These are the three common units for velocity, for angular velocity. If it is given in degree, you have to change it to radian per second. This is the SI unit system that we use. Changing degree to radian, you just multiply it by pi over 180. Or if you need to change revolution to radian, each revolution is the whole circle, so that's 2 pi. You just multiply it by 2 pi, and then you get radian per second. So you need to do radian unit conversion if you need to. Then the next would be the angular acceleration. The definition of angular acceleration is the same. We show it by alpha, so omega or theta dot. Alpha would be d omega over d t. Omega is already d theta, so that would be the second derivative. Also, we can call it theta double dot. So alpha, theta double dot, omega, theta dot, and then the unit is radian per second. So we can see right at the bottom of this. So like acceleration, we can define deceleration if alpha is in the opposite direction of omega. If our omega is in this direction here, and our alpha is in the opposite direction, that alpha we can refer to as deceleration. So if alpha is in opposite direction of omega, then alpha is referred to as angular deceleration. Now we are going to develop the kinematic equations for rotation. So kinematic equations for rotation. Omega is d theta over dt. So if I rearrange it, that would be d theta would be omega dt. So that's the first equation that we have. And we can take an integral between theta dot and theta. And here time changes from 0 to t. If omega is constant, if omega is not function of time, then we can take it out of the integral, and our equation will be developed for constant omega. So let's write it here. If omega constant, and that's the big if, you need to remember that. So theta minus theta dot plus omega t, and I move theta dot to this side. So that's our first equation for rotation. And if you look at it, this equation is very similar to, let's say, x dot plus vt, to the linear relationship. So I'm just writing here for comparison to see the kinematic equations are very similar. Alpha is d omega over dt, we do the same thing, we rearrange it. So we have d omega alpha dt, changing from 0 to t here, omega not initial to the final. If again, here that's the equation that we have and we have to use. But if alpha is constant, if alpha is not function of time, then equation becomes simplified. So if alpha is constant, if omega equals omega naught plus alpha t, and that's our second equation. And this equation is only valid when alpha is constant. This equation is valid when omega is constant. And then similarly, we can compare it with the kinematic equation that we knew before. And here I'm just writing this equation for comparison. So we can develop another kinematic equation for independent of time. So if alpha, here, we have developed two equations so far. If alpha is d omega dt, and omega is d theta over dt, I can take, we have time in both equations. I can find time from one equation and replace it into another one to remove time from my equation and get in an equation independent of time. So here, dt would be d omega over alpha. If I plug dt over here, I will get omega dt, which would be d omega. And I move it over there, alpha d theta. So that's the equation that I have, independent of time. And you can see it's in a derivative form. Again, if alpha is constant, I can simplify that. Let's say omega not omega. Here would be theta not theta. So omega d omega would be half of omega equals alpha theta minus theta naught, or usually written in this format, 2 alpha. So this is our third equation, or equation independent of time. Again, this is very similar to kinematic equation for linear velocity. I'm just writing it here for comparison. Just I write compare to see that they have the same format. And you can only use this equation if alpha is constant. Again, if alpha constant. So that's our third equation, and also we can develop our fourth equation for constant angular acceleration, alpha t squared. And that would be our fourth equation. And I write the other form for the linear form for comparison. That technically you don't need to memorize any new equation. You just need to all the equation that we developed for kinematic equation that we developed for a linear velocity and linear acceleration are true for angular acceleration and velocity as well. So the only important note is that you need to remember you can use these equations if the assumptions that we use for developing these equations are true. The assumption for this equation was that omega is constant. Here alpha is constant, alpha is constant, alpha is constant. If it's not constant, that is fine. You just need to use the integral format. If omega is function of time, is alpha function of time. Here, if alpha is function of theta instead of time, then we could use this equation, which is independent of time. Now I'm going to use I'm going to develop relation for between linear velocity and linear and angular velocity. So let's say again, I draw my disk here. Let's say it has a radius of r. The displacement is d theta. This is a small, I hope you can see it. D theta, that's d theta. And then this arc length would be ds. The derivative means very small. So the position, if you start by the position, is ds equals r d theta. That's the angular position, and that's the linear position, ds d theta. So they're related by r, they're proportional by the radius. Velocity, again, the definition of velocity is ds over dt. And ds is r d theta. So you have r d theta over dt, so r omega. So if you want to find a velocity, let's say you want to find velocity here, I'll just write it a little bit bigger so you can see velocity is again proportional to angular velocity by the radius, v r omega. In a vector form, you have velocity omega cross r. So that's the cross product. I mean, here it gives you the magnitude of velocity, but in a vector form, it gives you the direction as well. The result of a cross product is a vector. The velocity is a vector, angular velocity is a vector, and the radius would be a vector. You need to remember that the cross product is not commutative, which means that you can't change the order. Here, omega cross r is not the same as r cross omega. So let's write that. It must be noted that cross product is not commutative. Therefore, omega cross r is not the same as r cross omega. So that's a common mistake I see students make. They change the order, r omega, because we usually write r omega when we are dealing with a scalar form, but in vector form is omega cross r, and it matters which one you write first. So in terms of, if I draw our disk again, if this is r, and let's say this is rotating by an angular acceleration of omega, then the velocity here at this point, let's call it p, would be v. If I want to write it in a vector form, omega here, because it's rotating counterclockwise, so it's going to be positive k. If my axes are x, y, and z, omega would be in the direction of positive z. So x and y are radial and z is coming out of the surface. And then if you want to identify the direction of omega, is you're rotating your hands in the four fingers are in the direction of rotation, and then your thumb would indicate the direction of the vector direction. So omega would be k. So if I want to write velocity here, the definition of velocity is omega. So omega cross r omega in a vector format would be omega k. Cross r in a vector form, it would be in the direction of x. So it would be I. So I write it Ri. So omega cross R. So K cross I. Either you can write the definition of cross product in a matrix format, or you could use this circle definition to find the answer for your cross product. Ijk positive, which means that I cross J would be K if the order is in the counterclockwise direction. K cross I would be J. In the opposite direction would be negative, in the opposite direction of the arrow. So J cross I would be negative K. Here, going back to what we have written, K cross I. So K cross I, I'm moving in counterclockwise direction, which is the positive. So that would be equal to J. So I can write R omega J. So my velocity would be in the direction of positive J. If I go back, I can see that visually, by visual inspection, also the velocity is in the direction of positive J, is in the direction of Y. If omega is in Z direction and R in X direction, velocity would be in J direction. To just expand this circle, that's probably, some of you might not have seen this before. So I cross J would be positive K. J cross K would be I, and K cross I would be J. And if I move in the opposite direction, let's say I move in K cross J in the opposite direction, would be negative I. J cross I would be negative K. I cross K would be negative J. So that's a kind of a shortcut for finding a cross product if you don't want to write the cross product definition of I, J, K, and writing the second row would be the first vector here, which would be our omega. So it only has K components, so it would be omega. And then the third row would be our second vector, which is R, and it only has I components, so the rest would be 0. So I would be 0, no component in I, 0 minus 0. J is a negative. If I remove the second column and the first row would be 0 minus R omega. And K would be 0 minus 0. So if you look at here, that's the only component that we have, negative, negative, so it would be R omega J, which we already found over there. For this simple scenario, you could use this definition. If you can see, if you understand this semicircle is pretty easy and straightforward. But if you're more comfortable with the conventional cross product relation of writing IJK and finding the determinant here, that's acceptable as well. So here we talked about the velocity, R omega. The velocity have one component. In a vector format is omega cross R. The order is very important, so pay attention. Omega is the first vector that you need to write. Now let's go to acceleration. So now we are developing the relation between linear and angular acceleration. So acceleration. Definition A is dv over dt, derivative of velocity over time. Velocity, we found that is proportional to angular velocity. So omega cross R. And if I want to take a derivative, because I have two components, I have to take a derivative of the first component times the second one plus the derivative of the second component times the first one. So let's do that. D omega with respect to t cross r plus the first component dr over dt. So can you tell me what is this fraction, the derivative of omega with respect to time? That's true, that's alpha, the angular acceleration. What about this component, the derivative of r with respect to time? And r is the radius time, that's velocity. So I can simplify my acceleration equation A. I can write alpha cross r plus omega cross v. I can further simplify this equation because I know velocity is omega cross r. So for A, the first component, I write it as it is, alpha cross r. Alpha is angular acceleration, r is the radial distance, the radial vector omega cross v is already omega cross r. So that's my acceleration, the acceleration that I will have based on the rotation about a fixed point. So I have two components. The first component would be AT, would be the tangential acceleration. The second component would be AN, would be the normal acceleration. So if you have a disk rotating about 0.0, and this is R, if you have omega as well as alpha, so if you have alpha acceleration, angular acceleration as well, you're going to have AT, the tangential acceleration. Also, you have AN, which would be in the direction of the center or the opposite direction of your radius. So I'm going to call this AN, AT and AN. Have two components, AT and AN. AN is in the direction of negative R, so towards the center. If R is in this direction, AN is in the opposite direction. So let's write AN is in the direction of negative R. Direction negative R. In a scalar form, AT alpha cross R, in a scalar form, AT is just simply R alpha. And AN, if you look at it here, omega cross R, omega cross R, the result of two cross product would be a vector that is perpendicular to both, and then another cross product. This result would be in the negative direction of R. So negative R omega squared. You have two omega, so it would be R omega squared. That's a scalar form. Well, a scalar form, as you can see, is much easier if we have a 2D that we could identify the directions by just inspection, then that's easy to use a 2D. But in problem that is difficult to visualize, what would be the acceleration, and omega and R have multiple components, we have to use the vector form. So for a problem, let's say this is disk, and this disk is a 2D problem. So for this disk, you know, if the alpha is in this direction, then AT would be in this direction, and AN would be in that direction. So it's pretty easy by inspection to identify the direction of both components of acceleration. And this acceleration the normal component of acceleration is very similar to the acceleration that we developed previously for tangential and normal coordinate. Do you remember the centripetal acceleration? It was v squared over r. And what is v? Velocity. We can v is r omega. So it's r squared omega squared over r. If I cross r here, it would be r omega squared. So you can see both of them are talking about the same thing. Over there, we show it as velocity squared over r. Here, we show it r omega squared. And both of them are in the direction of the center, or the opposite direction of the radius. Because we have two components of acceleration, we can find a magnitude of acceleration as well. And the two components are perpendicular to each other. So finding a magnitude would be easy. Magnitude of acceleration. The square root of AT squared plus AN squared. So you need to remember in rotation of a rigid body, you have two components of acceleration, AT and AN, and then one component of angular acceleration. For velocity, it's only one component. For velocity, it's just r omega, or omega cross r in a vector form. This is so we have an acceleration equation, alpha cross r plus omega cross r. The result of a cross product would be a vector. Another cross product, a vector. Here is a vector, A is a vector. Here for velocity, omega cross r. That's it for today's lecture. In the next lecture, we'll be solving problems of kinematics of rigid bodies.